Welcome to Wonderful Morning of Chem 1211 with your host, Dr. White. All right, yesterday I went through and did the lab. Make sure you watch the video. I showed how to do the calculations in that video for yesterday's lab. Also, coming up, test number 1 in a while, keep up to date. Do the practice problems. Remember, the practice problems help you do good on my quizzes and tests. And test number 1 coming up, the old test number 2, is probably the hardest of the semester. So keep up. All right, I promised today I do chapter 10 problem set. And I just remembered I've got to open up a periodic table. And the periodic table's opened up. So let's look at chapter 10, practice problems, part 1. Now, you should see on your screen now what ions will the following elements form. How do you do that? You go to the periodic table and find out the atomic number. The atomic number gives you how many electrons and protons. And if we look at a periodic table, the first one is what ion will sodium form? And sodium has a atomic number of 11, and it wants to have the same number of electrons as the nearest noble gas. In this case, that's neon, because you have two choices, argon or neon. And neon is 1 away, 11 to 10, or 11 minus 10 is 1. Argon, 18 minus 11 is 7 away. So it wants to have the same number of electrons as neon, 10, but it still has its 11 protons. So what does this mean? It will go from 11 electrons to 10 electrons. It will still have the 11 protons. Each electron is a -1 charge. Each proton is a +1 charge. Do the math, add it up, and what do you get? +1. And the way you show the ion, not just putting the number, chemical symbol, superscript to the right, that means above, and in the case when the number is 1, we just show a plus sign. Now, let's look at calcium. And calcium, we go to our periodic table, has atomic number 20, and the nearest noble gas is argon, 18 away, or not 18, atomic number 18, 2 away. If you notice, krypton is 16 away. So which is closer numerically? Argon. So you want to go from 20 20 electrons, 20 protons. Wait, I got that right. Let me check. Yep. All right, let's go back to my whiteboard. All right, so we're at 20 electrons, 20 protons. Calcium wants to go to 18 electrons, 20 protons. Each electron has a -1 charge. Each proton has a +1 charge. Do the math. -18 plus 20. Add these together and you get a +2. But the question asks what ion is formed. So we have the chemical symbol and superscript +2. Now, this is the old way of doing it, which I still like. You can also write it, like you'll probably see in your book, 2+. Now, let's do one more. Let's do oxygen. What ion does oxygen form? And if we look at our periodic table, let's go there. You'll see oxygen atomic number 18. And what's the nearest noble gas? Well, neon is 2 away, helium is 6 away, and argon is 10 away. How do I do that? I look at the atomic number and the difference. You want the smallest difference. Therefore, for oxygen to be happy, have an octet, it will go from 8 to 10. So it has 8 electrons, 8 protons. It wants to be stable, so it will go to 10 electrons, but still have 8 protons. Remember, each electron is a -1 charge. Each proton is a +1 charge. Do the math, and we have -10 plus 8. Add them together, we get a -2. Now the question asks what ion is formed, and you show that by a chemical symbol, superscript to the right, the charge. And here's the charge. So that'd be -2, or the newer way, which I don't like, 2-. Either way is correct on my test. Now, interesting thing, once you know one ion in a family column, you know them all. So if we've done calcium, it's a +2. Magnesium, which is in the same column, will also be a +2. If we look at oxygen, a -2, then sulfur will be a -2. Now, it turns out chlorine is a -1 if you do the math. And guess what charge bromine has? What ion does it form? -1 bromine, Br-. So remember, when you know one in a column, you know them all. Now, the next question is, what's the empirical formula for molecules with the following ions? And notice I have written there, remember, all molecules have a net 0 charge. So let's look at these. How do you do this? Let's look at C. What would be the empirical formula of calcium +2, chlorine -1? So the question is calcium +2 and chlorine -1. Well, how do you do that? All molecules have a net 0. Let me make this a little wider. Charge. So what does that mean? Calcium is a +2. chloride ion is a -1. This has to equal 0. It doesn't. So how do you do that? You cannot change the charge, excuse me, but you can change how many. To get this to 0 plus 2, we need a -2. Therefore, we multiply that like that. And what does that mean? The empirical formula, 1 chlorine and 2 chloride ions. Good morning, Anna.
Hi, sorry for being late.
Don't worry about it. I started without you. You just go
Thank
back
you.
and watch the video.
Yeah,
All right. So that's how you do. Let's do another one. We're going through problem set 10, part 1. And the question is, what is the empirical formula for molecules of the following ions? Now, we just did calcium chloride. Remember, all molecules have a net 0 charge. Let's do magnesium plus 2 OH, which is hydroxide, -1. So the question is, what would be the simplest empirical formula for this molecule? And I'll do this one. I'll let you have one to try too, because I share. And, oops, that's not what I want. Magnesium is a +2. Hydroxide, polyatomic ion, is a -1. And as I have written here, all molecules have a net 0 charge. So when you add up the charges, it has to equal 0. It doesn't. Well, if this is a +2, this should be a -2. You can't change the charge, but you can change how many there are. And I'll put 2 there. This is a +2, 2 times -1, -2, and it will add up to 0. Now, what does that mean in terms of the empirical formula? Well, there's no number in front of the +2, so you have 1 magnesium. Now, how do you do, because number in front of the hydroxide is 2, how do you do 2 of those? Well, you put it in a bracket like this, and then subscript to the right, it'll close the right end here, you put the number 2. And that's the simplest empirical formula. So it's time to let you have some fun. And let's do F. What would be the empirical formula for an ion or for a molecule with the ions magnesium +2 and nitrate -1? Your turn. And when you're done, give me a thumbs up. All right, I should get started. Remember, all molecules have a net 0 charge. So what does that mean? You have a +2 for magnesium and a -1 for nitrate. This is the nitrate polyatomic ion. All molecules have a net 0 charge, so this has to add up to 0. It doesn't. So what do? Well, we can't change the charges, but we can change how many. If this is a +2, I need a -2, So I'll put a 2 in front. Now remember, there's a 1 in front of that plus 2. So that means there's 1 magnesium. And now we have our NO3 nitrate, and we need 2 of them. We put it in a bracket, and to the right subscript, we put the number 2. Oh, this is fun. Let's try one more. What would be the empirical formula, excuse me, for the molecule containing sodium cations, and this is called sulfate anions? And it's your turn. Remember, all molecules should have a net zero charge. And give me a thumbs up. I might have missed it because I had to blow my nose. But all right, everybody's done, so I better get to work. If we look at here, sodium is a +1 charge, and the sulfate anion is a -2 charge. All molecules have a net zero charge. So what do? Well, this is a -2. This has to be a +2. We can't change the charge, but we can change how many there are. And therefore, this tells us we have 2 sodium and 1 sulfate. And that's sodium sulfate. And that's how you do it. By the way, sodium sulfate is the chemical, one of the 2 chemicals that they can put in the little packets that you get in electronics and other things to keep it dry, and where it says, do not eat this. And that's what's in that packet. A couple of years ago, I had a general chemistry student who said, oh, when I was young, I ate those. I said, did you live? And she laughed. So did I. All right, let's move on. Next one is draw the Lewis structure. Ooh, and circle all double and triple bonds. How do you draw a Lewis structure? You take the valence electrons. And remember, all atoms want an octet, except hydrogen's octet, octet means 8, is 2. That's the one exception. So if we look at ammonia, NH3, how do we do that? And you're asked to draw the Lewis structure for ammonia. Well, first of all, for a Lewis structure, you need to find valence electrons. And how do we do that? We look at our friendly neighborhood periodic table, and the number at top tells you how many valence electrons. And hydrogen, all the way over here, has 1 valence electron, and nitrogen has 5. You don't look at the atomic number for valence electrons, you look on top. So nitrogen has 5 valence electrons, hydrogen 1 valence electron. Notice there are 3 hydrogens, 1 nitrogen. And the only way you can make this work is putting nitrogen in the center. Now I'm doing it the long way. You don't have to do this. Notice nitrogen says I've got an unbound electron, you've got a single electron, let's share. And it does it here and here, and it does it here and here. And therefore, when it shares, it would look like this. Remember, two dots, a pair of electrons is a single bond. And this has three single bonds. Remember, types of and you should know this chart. Hint. A single bond has one pair of electrons, double bond two pair, and triple bond three pair. You know you're a baseball, when you get a single, you go to first base, one. Excuse me. When you get a double, you go to second base, two. And when you get a triple, you go to third base, three. So single bond has one pair of electrons, double bond two pair, and triple bond three pair. So what does that mean? Let's try, and I'm going to do one, then I'll let you do it. Nitrogen gas. And how do you draw the structure for nitrogen gas? Well, you look at this and say, each nitrogen has 5 valence electrons. Remember the number on top of the column. Well, if I draw each nitrogen Lewis structure of the element, here we have it. And this nitrogen says to that one, I have 3 single electrons, you have 3 single valence electrons, let's share. And they do. Now, the non-bonding electrons right here and here come along for the ride. And what kind of bond exists between nitrogen atoms and nitrogen gas, NO2? Well, count the pair of electrons. 1, 2, 3. Oh, look, someone put a nice chart up. And 3 pairs of electrons is a triple bond. And the problem, it said circle all double and triple bonds. So you would have circled this. Now, I'm going to let you have a chance to try it. Draw the structure, Lewis structure for oxygen. Now, I'm going to help you out. You need to find the valence electrons for oxygen. If we look at our friendly neighborhood periodic table, oxygen, look on top, number 6. And therefore, oxygen has 6 valence electrons. And now it's your turn. Why don't you figure out why don't you draw the Lewis structure for oxygen gas, which you're breathing in now and out and keeping you alive? And for those who came in late, I mentioned earlier that yesterday's lab, excuse me, must be the cold weather. It's getting to my throat. Anyways, was cold out there this morning, last night. I actually turned up my heat a little when I got up this morning. But anyways, don't forget, in the video yesterday, I showed you how to do the different calculations for the various values you need to calculate for yesterday's lab. And it's in there, so go back and look at the video if you need to learn how to do those calculations with dealing with specific heat of a compound, in this case, the metal rings. All right, let's get to work. Now, how do you do this? Each oxygen has 6 valence electrons. Now, you don't have to do it this way, but I'm showing you the thought process. This oxygen says, oh, I have 2 single electrons, valence electrons, and you have 2 single electrons. Let's share. And they do. And now the non-bonding electrons on each oxygen come along for the ride. And here we have it. Now, something I didn't do here, which I should have, and I'll do right now here. If we look at this oxygen in red, it has 8 valence electrons. 2, 4, and 4 more is 8. And same thing for this side. Now, what kind of bond is this? And if we look at that, how many pairs of electrons are being shared? By the way, tough part of math in this class, you have to know how to count. And a pair is 2, so they're 2 pair. And what kind of bond is that? Oh, look, 2 pair of electrons, that's a double bond. And you were asked to circle all double bonds or triple bonds, so you would have circled that, because that's a double bond. Now let's do one more, and I'll do this one, and you practice it on your own. Let's do KCN, potassium cyanide, and you should practice sodium hydroxide on your own. And if we look at potassium and carbon and nitrogen, we'll see potassium is here. At first, you'll say, oh, it's got 1 valence electron, which is true. Carbon has 4, nitrogen has 5. Now, while we're still at the periodic table, this is something important you should remember, and that is all elements in the first 2 columns, the alkali metal and the alkaline earth metals, never, ever form covalent bonds. They don't. But they do form ionic bonds. So you have to know what ion is formed. We already did this. Sodium, potassium, and lithium form a +1 ion. So we need to do KCN, potassium cyanide, thank you, Hannah. on your screen. I don't know if you can see it, but one of your colleagues just found a nice link to how to do these type of problems, or knowing what are metals, what are non-metals. And the metals, I don't know if all metals, but most metals form ions, not covalent bonds. So what does this mean? We have a potassium, but you don't look at the valence electrons. You know that's going to form the +1 cation. Carbon has 4 valence electrons, nitrogen 5. And carbon looks at nitrogen and says, oh, you've got 1, 2, 3 unpaired valence electrons. I do too. Let's share. And they do. There's still 1 left over on carbon, and the nitrogen non-bonding electrons are still there. Now the potassium has lost this valence electron. That's why it forms this cation. And where does it go? To here, the carbon. And this now has an extra electron, so it will be a -1. This is a +1. So between potassium, and this is called the cyanide anion, negative charge, there's an ionic bond. And if you notice, between carbon and nitrogen, what type of bond is that? Count the pairs of electrons. 1, 2, 3. And if we go up here, someone wrote a nice table. 3 pair of electrons is a triple bond. So this right here, you would circle, because that's a triple bond. But remember, all alkali metals and all alkaline earth metals always form a cation. That side will be cations, a plus charge. All right, let's move on. And the question is, number 4, what is the simplest empirical formula for covalent molecules with the following elements? And remember, all elements except for hydrogen want an octet. So how do we do that? Let's look at water. What would be the simplest? I just gave it away. I think I just gave it away. Simplest empirical formula, covalent molecule between hydrogen and oxygen. Well, hydrogen has 1 valence electron. Oxygen has 6 valence electrons. Now, one way of doing it visually is saying oxygen has 6, it wants to get to 8. How many valence electrons does it need? 2. If each hydrogen can only give 1, and oxygen needs 2 valence electrons, you need 2 hydrogens. And since you need 2 hydrogens, the empirical formula would be that, which is H2O. Uh-oh, my O didn't want to stay there. Now it does. All right, let's try the following. What would be the empirical formula of a molecule with carbon and hydrogen? Now here, you can look it up, but carbon has 4 valence electrons. Hydrogen still has 1 valence electron. And the question is, what's the empirical formula? Remember, carbon wants an octet, and it's your turn. And when you're done, give me a thumbs up. All right, let's do this. Now, carbon has 4 valence electrons. Hydrogen has 1. Carbon wants to get to 8 valence electrons. And how does it do that? It gets valence electrons from hydrogen. Well, if it's at 4 and it wants to get to 8, it needs 4 hydrogens. Now, it would look like this, but this is not what I'm asking you to do. What does this mean? There's 1 carbon and 4 hydrogens, and that's how you do that. And
Sorry, can you just tell me one more time why carbon wants to have 8 valence electrons?
yeah, you should have 8 valence electrons around carbon, but hydrogens too. Do you want me to do it? You want me to have you do another one?
Yeah, I just don't know why is it 8.
Well, that's because it has the most stable number of valence electrons, the same as the noble gases, which
Okay.
are very stable. In
Yes.
fact, until about
So that's why we always need 8.
mhm,
Okay.
until about, I don't know, it's maybe only 20 years ago. I might be off by 5 years. I think it was in the 1990s somewhere, a little over 20 years ago. Back in the 1970s and 80s and part of the 90s, the last column of the periodic table was called the inert gases. And the reason at that time they were called inert gases, because they didn't react. They were stable. They were happy with their 8 valence electrons, 8 octet. And other elements wanted to be stable like that, so they would get an octet. Now, it turned out about 20, 25 years ago, a very creative and smart chemist found a way to make the inert gases react. Well, if you can find a way to make them react, you really have to beat on them hard. I mean, really hard. They're hard to react, but he did find a way. So we couldn't call them inert anymore, but we call them Nobel gases now. Now, the Nobel gases, or Noble, I think it's named after Alfred Nobel, but I don't know. The noble gases are very, very unreactive, but we can't say they're inert because someone found a way to make them just a tiny bit reactive, but they're still the most stable. And that's why you have the octet rule. Now, let's try another one. What would be the empirical formula for a molecule with nitrogen and hydrogen? And I'll help you out. Nitrogen has 5 valence electrons, hydrogen 1 valence electron. Remember, the octet for hydrogen is 2, but the octet for everybody else, all the other elements, is 8. Your turn. And when you're done, give me a thumbs up. All right, everybody's done, so I better get to work. Now, you don't have to do it this way, but it helps. There's another way, but most students find this. Nitrogen has 5 valence electrons. Hydrogen has 1. Nitrogen says, oh, I've got 3 unpaired electrons, or I'm at 5. I'd like to go to 8 valence electrons. How many more do I need? 3. If each hydrogen can only give 1 to get 3 of them, I would need 3 of these. And I'll show the Lewis structure. And now nitrogen, if you count all the valence electrons, says 8 valence electrons, it's happy, but I asked for the empirical formula. This is the Lewis structure. But I asked for the empirical formula, which is 1 nitrogen and 3 hydrogens. And this is the empirical formula. Which is the answer. And that's why, oh, by the way, this is called ammonia, NH3. And I see one of your colleagues said, and the answer is yes, you could do it that way. Your colleague asked, if you want to get to 8 and you, excuse
Bless
me,
you.
thank
You
you.
need a tea or something.
But anyways, you can subtract, you want to get to 8, subtract 5, that means you need 3 valence electrons. And where do you get them? From the hydrogen. Hydrogen only has 1. To get 3 valence electrons, you need 3 hydrogens. And that's how you do it. And we're done with the practice problems. Any questions on any of that?
No, I think we're good. Is this going to be on the test?
Yes, it could be.
Okay.
This would be the first test, which you'll have to take a COD. Let me open up something which I didn't have opened up. All right, you should see on your screen from important information, it's labeled test 2, but it's really test 1. And we were talking about yesterday the concepts that 1 mole of an element equals the atomic weight of that element in grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight is the sum of all atomic weights. So this is a very important concept. Now, because I've cut down on memorization, you don't have to memorize this, but you do have to know how to use this. So if we look at this, again, 1 mole of a compound equals the molecular weight of that compound. And what is the molecular weight of a compound? That's the sum of all atomic weights. And where do we find the atomic weights? You go to your friendly neighborhood periodic table. And remember, I will have on test 1 and quizzes 3, 4, 5, and 6, and test 2, it will say underneath your name, please use proper significant figures for all calculated answers. And it will say, please use all atomic weights or masses. Well, I think I use weight, I like that better, to 3 significant figures. And if we look at carbon, 12.011, how do you round that off to 3 significant figures? Keep the 1, keep the 2, 2, I was gonna say 12. Anyways, keep the 2 and keep the 0. Those are my 3 significant figures. Use the 1 to round off, and that would be 12.0, because 1 is less than 4. You drop the 2 ones. Now, if we look at chlorine, 35.453, the 3 significant figures, keep the 3, keep the 5, keep the 4. That's my 3 significant figures. The 5 used to round off, that's 5 or higher. So I drop the 5 and 3, increase the 4 by 0.4 by 0.1. So the answer would be 35.5. And if I look at the clock, which I just did, it's time for a 5-minute break. I'll see you in 5 minutes at 9:55. Let's take a break. Time to get going. Welcome back. Let me remind you, tonight I have my office hour. Remember, I have new office hours on Tuesday and Wednesday night from 6 to 7:15, the same Zoom login. And if you have any questions, or you need any help, or if you need any practice with anything I've covered in 1211, stop by and I'll help you. Again, it's the same Zoom login, so you don't even have to get in your car and drive to COD. I'll be here like I am now. All right. Now, we were talking about the mole concept. And the reason I'm going to be going over it again right now a couple of times is it's a very important concept. And it's used very widely in chemistry. But to make it relevant to you, you need to know it to get a good score on test number 1, quiz number 3, quiz number 4, quiz number 5, quiz number 6, test number 2, and the final. If you don't know how to convert from moles to grams and grams to moles, you're going to lose a lot of points. I don't want that to happen. So that's why we're going to practice it some more right now. All right, I'll do one, and then we'll do one stepwise where you'll do it too. So the first thing, when you have a problem like this, and take a deep breath, let it out, take a deep breath, let it out, stay relaxed. This is called a word problem because it's got words. Profound. But anyways, what I always like to do and have taught my students, and it's helped them immensely, is first of all, find out what are you being asked to find. And notice it says how many grams of water. I don't know where I came up with the question mark, but I've been using it, and students find it very helpful too. Now, what are you given? Well, there's only one thing we're given. This, and don't forget to put the units. Now, to proceed, once we've done this, we don't have to look at the word problem again. Well, there's only one number I have to start with. And that's the moles of water, 1.437 times 10 to the third moles of water. And what do I want my answer? If I could do this in one step, mathematical formula, relax, you'll see how to do this. What units do I want my answer to be in? And I'll keep an eye on not making yesterday's mistake. You look at yesterday's video, right before I made my mistake, I have now a little warning. I didn't say, well, I should have put warning. But anyways, Dr. White makes a mistake and corrects it too. But anyways, I won't do it now. Look at what units we're trying to get to. Grams of water. Now, if we had some kind of conversion ratio, something over something, what would that be? Well, it's time to use your good buddy, your good friend, unit analysis. And it has been my good buddy, good friend for many, I hate to say this, decades. And how does it work? Whatever you're trying to get to, units go on top. Whatever units you don't want in your final answer go underneath. Remember, anything divided by itself cancels out because it equals the number 1. And now I'll write those units in. And where do I get these numbers? Well, where do I find a relationship between moles of a compound water and grams of a compound? Well, if you look at important information, test number 1, 1 mole of a compound equals the molecular weight of that compound. Well, where do we get the molecular weight? Well, the molecular weight of the compound is equal to the sum of all atomic weights. Ooh, I've got to find the atomic weights since we're dealing with water, hydrogen, and oxygen. And where do you get those? From your periodic table. Remember, use 3 significant figures for all atomic weights. Hydrogen is 1.01 to 3 significant figures. Oxygen, 15.999, rounds off to 16.0 for 3 significant figures. So we need the molecular weight of water. And that's 2 hydrogen, 1 oxygen. And now that's 2 times the atomic weight of hydrogen to 3 significant figures is this. And this is 1 times the atomic weight of oxygen to 3 significant figures is that. Do the math. Add them together. Remember, you have the same number of significant figures to the right of the decimal as the number you're adding that has the fewest. This has 2 to the right of the decimal. This has 1, which is the lowest number. Hopefully you pick 2. What I say? Hopefully you pick 1. Hold on, I've got to reboot. All right, hopefully you pick 1. And how do you round this off to 1 to the right of the decimal? You keep the 0 and you use the 2 to round off. That's 4 or less. I'll drop it. So the molecular weight of water is this, but we're not done. How do we know what numbers to put here? And when you have A equals B, you have 2 ratios. And where do we get this ratio for this? 1 mole of a compound equals the molecular weight in grams of the compound. In this case, what's the compound? Water. So 1 mole of water equals the molecular weight of water, which is what we just calculated. Now, before I pick up my calculator, I shouldn't pick it up. Bad Dr. White. Anyways, I'm going to check my units. Notice we have moles of water divided by moles of water. And anything divided by itself is the number 1. So this cancels out. What units are we left with? Grams of water. Is that what we want? Yes. So we're on the right track. Now I'm going to pick up my calculator, turn it on, make sure it's clear. I have 1.437. And now for a calculator, mine, second key, double E, and you'll see the E on there. I don't know if you can see it. We went through this before. And I have 3 times 18.0. And when I do that, my calculator gives me this number, Let me write that 8 a little better. This. However, it will say on test number 1, please use proper significant figures for all calculated answers. So for multiplication and division, you get the same number of significant figures in your answer as the number you're multiplying and dividing that has the fewest significant figures. This number here, count all non-zero numbers, 4 significant figures. This number here, well, I've got 2 non-zero numbers, but a 0 at the end with a decimal is significant, so this would be 3 significant figures. This 1 is an exact number and plays no role in determining significant figures. So which is the lower number, 4 or 3? Hopefully I'll pick 3. So now round this off to 3 significant figures. Keep the 2, keep the 5, keep the 8, use this to round off. And notice this is 5 or greater. I'm going to drop that, increase this by 1. So the correct answer if we have these many moles of water, we'll have these many grams of water, and that's a 9. Let me erase it and do it better. And that's how you do it. All right, let's do another one. All right, we're going to do this stepwise where I'm going to help you and you're going to help me. And I need some help. What are we being asked to find and what are we given? And why don't you draw that, write that on your piece of paper right there. And when you get that, give me a thumbs up. All I'm asking is, what are we given? What are we being asked to find? All right, time for Dr. White to get started. Well, we're trying to find how many moles potassium hydroxide. That's called potassium hydroxide. And it's important industrial chemical used widely in the United States and the world too. All right, what are we given? Well, this is the only number we have to work with. Don't forget to put the units. It's important. Once we have this, we no longer have to look at the word problem. So there's only one number we have to start with, this. Now, your turn. What units do we want our answer in? Why don't you write it over there? And when you're done, I'm not asking you to do anything more than figure out what units are we being asked to find. And when you're done, give me a thumbs up. All right. How do you figure? Well, you already figured that out. It's right here next to the question mark. And that's moles of potassium hydroxide, KOH. Now, if we could convert this in one step with a ratio, it's time to use your good buddy, your good friend, unit analysis. What units, not numbers, should go up here? And when you're done, give me a thumbs up. All I'm asking you is to write the units that go above and below. All right, my turn. And using your good buddy, your good friend, unit analysis, whatever you're trying to get to, the units go on top of this ratio. Whatever you're trying to get rid of, the units go underneath. And now I'll write those in. Now, where do we get the numbers that go in that ratio? Well, if you look at important information, test number 1, which I have to redo on the blackboard, you'll see 1 mole of a compound equals the molecular weight of the compound. And also, I'll write here the molecular weight in grams of the compound equal the sum of the atomic weights in the compound. So in order to fill in here, I need the molecular weight of potassium hydroxide. And how do you do that? Well, you need the sum of all the atomic weights. There's 1 potassium, 1 oxygen, 1 hydrogen. Well, how do you get those atomic weights? You go to the periodic table. Now, I'm going to let you try this one, and then I'll do it. For potassium, K, what's the 3 significant figures, the atomic weight? And give me a thumbs up when you think you got it, and I'll tell you what it is. All right. How do you do that? Keep the 3, keep the 9, keep the 0, 3 significant figures. And if I look at this, the 1 to round off is 9. That's 5 or higher. I drop the 9 and 8, increase the 0 by 1 to 0.1. And for oxygen, it's 16.0, hydrogen 1.01. So that's 39.1. These are the atomic weights. To 3 significant figures. And if I do the math, I have 56.11. However, when you're adding, you have the same number of significant figures to the right of the decimal as the number with the fewest. This has 1, this has 1, this has 2. What's the lowest number? And time's up. Hopefully you pick 1. Now, round this off, and then I'll do it to the proper number of significant figures, 4 in addition. And when you've done that, give me a thumbs up. All right, you guys are fast today. Thank you. So we want to have 1 significant figure to the right of the decimal. Keep the 1, use this 1, use this 1 to round off. It's 4 or less. I'll drop that. And the molecular weight of potassium hydroxide, KOH, is this number. So how do we proceed? 1 mole of a compound equals its molecular weight. And now we put those numbers in, because remember, if A equals B, You have two ratios. They're not equal. They're just two separate ratios. We can always write. And that's where these numbers came from. And now, before I pick up my calculator, I'll check to make my units. Do I get the correct units for my answer? Well, let's find out. Grams of KOH will be divided by grams of KOH. Remember, anything divided by itself equals the number 1, meaning it cancels out. What am I left with? Moles of KOH, and that's what we're trying to find. Now, time to pick up my calculator, clear it. And my calculator gives me this number. However, on test number 1, it will say, please use proper significant figures for all calculated answers. And why don't you figure out how many significant figures and what you should round this off to? Your turn, then I'll do it.
Can you just show me one more time how to use the calculator? Because I have like weird answers and I don't know why. I have like 0.15 and you have 1.54.
All right, do you have it in scientific notation?
Yeah, I have the same as you do.
All right, let's do it again.
Mm-hmm.
Clear it. That's the important thing. Always
Yeah.
remember to clear it. Put in 8.65.
Mm-hmm.
I don't know if you can see it or not. Then the divide right here,
Mm-hmm.
and then 56.1.
Yes, and I have 0.15.
You're not in scientific notation. That's why.
Okay, so I'm
All
pressing
right,
send.
all right, hold on.
Okay.
Stop. You have the calculator.
Mm-hmm.
Blue key, or whatever the second key is. And then right next to it, above where it says SCI/ENG, press
Mm-hmm.
it. Do you have SCI underlined?
Yes.
All right, hit enter. And it should clear it. Let's clear it.
Okay.
Let's do the following. Let's take 5 and divide it by 500. And do you get 1 times 10 to the minus 2?
Mm-hmm.
I don't know why, if that does, let's go back and try 8.65
Times
divided
56.
by
Okay.
56.1.
Okay, now I know. So which is
You
like
weren't in scientific notation.
yes. Okay, now I know.
All right,
Thank you.
now, hold on. Now, if you look at your calculator, underneath the number you just got, do you see the letters SCI very small?
Yes. Mm-hmm.
If you don't see that, you're not in scientific notation.
Okay.
Okay, and thank you for your question. All questions are good questions in my class and in my world. Or as I like to say, there's no such thing as a dumb question. All right, now, we're still, why don't you round this number off to proper significant figures? Oh, I gave it away. And then I'll do it. Tell me when you're done. Thumbs up.
Okay, so like in that case, do we need to like multiply by 10 to the minus 1 or no?
No,
Or we just
no,
leave it?
no,
Okay.
no. we're trying to round it off. Let me do it, all right? When you have multiplication division, you have the same number of significant figures in your answer as the number that has the fewest significant figures you're multiplying, dividing. Now, this first number, all non-zero numbers are significant, and there are three of them. So we have three significant figures. Now, one, because it's part of the definition, is an exact number, which plays no role in the determination of significant figures in your answer. Now, 56.5, all non-zero numbers are significant. And there are three of them. So what's the lowest number? Well, they're both the same, 3. So now you have to round this off to 3 significant figures. When you round off, you never change 10 to the whatever power. That always stays the same. So how do we round this off? Keep the 1, keep the 5, keep the 4. That's my 3 significant figures. The next number, which I put the double squiggly line underneath, is 1. That's 4 or less. When it's 4 or less, you drop that and everything after that. And you write now the number and remember 10 to whatever is not changed. And that's how you do it. And that would be your answer, 1.54 times 10 to the minus 1. Now, again, when you're doing multiplication division, which we'll do a lot in this class, your final answer should have the same number of significant figures as your whatever number you multiply and divide that has the fewest significant figures, and exact numbers are not used to determine significant figures. In this case, the 1 is an exact number. Okay? And let's move on. Now, I've done these. We've done all these converting. Now, I have here converting grams to particles. I should have cut that out because we'll never do that in this class. I've never done it. Some teachers have you do that. What you have to do is convert grams to moles and moles to particles. I've never had to do that in my life in chemistry, so just ignore this I have in yellow. All right. Now, I'm going to turn the switch. Will this be on a test to the off position? But I still want to briefly cover it. Now, there's something called percent composition. That's the percent mass of each element. And you can find that by how many of those elements and what's the weight. So if there's 3 carbons, you'd multiply 3 times 12. Now, the way you do percent mass of an element is mass of an element divided by the total mass or molecular weight of a compound times 100. There really shouldn't be a percentage there, but this is a formula. And a lot of times at my level, when you do analysis, which we won't do in this class, a percent carbon, nitrogen, oxygen, CNO or CNH in a molecule, you can have that measured, and that will help you determine, do you have the right empirical formula? So percent mass is how much by weight of each element you have in a compound. Switch was off. So now move on. Now the empirical formula we talked about already, that's the lowest whole number ratio of atoms in a compound. Now, one thing I neglected to mention, but I better now, this is always a whole number. And when there's no number, that's the number 1, which tells you there's 2 hydrogens, 1 oxygen, water. And this is sodium chloride. You know it as table salt or salt. And that's what you put in your food to season it. Or I haven't had in a long time because I need it like a hole in that. But if you have, you put it on your French fries. I can't remember the last time I had. Oh, I remember. It's been about a year and a half. I was at a friend's house. We picked up some hot dogs with French fries for lunch, and that's last time. And if you ever go out with chemists to breakfast, lunch, or dinner with someone like me, and I've done this, please pass the nickel when we want the salt. But anyways, notice this has 1 sodium, 1 chlorine, and you never will see 1.5. You can't. That's like saying, how many live people are in this room? Well, there's 2.5 people. No, you can't. It's only whole numbers. Now, here's a way of determining an empirical formula using moles, but click, I'm going to switch this off because I've never had to do this. And you won't. So we're switching that. Oh no, guess what? It's the end of this chapter 6. And what does that mean? It means new chapter time. And that new chapter is chapter 8. Now, one thing I noticed, which I apologize for, I should have cut out a lot from the beginning, because if you look at chapter 8, you should go back and look at this. I've also included this from chapter 6. They're sort of together. And I should have really gone here. We've done the formula or molecular weight of water. We've calculated some of these. We've gone through the mole. And remember, a mole is 6.02 times 10 to the 23rd. And this is called Avogadro's number. Here in the old days, I said you must memorize it, but I'll give that to you in important information. Test number 1. And what do we measure? Well, we've talked about moles of atoms, moles of molecules, and we've used this to do problems we've already done. And because 2 things are equal to each other, here are the 2 ratios we've already used. And we've done problems like this. You can go back and review this. Now here I have the old way without using a calculator. You get this, calculator will give you this number right here. We talked about the mass of a mole. 1 mole equals the molecular weight of that formula for a compound and of that atomic weight for an element. And we did problems already like this. I just did something like this. You can go back and look at this. And I've done this for different ones. We did similar, how many grams, and why don't you go back and look how I did this. And now we're up to speed. All right, like I said, I should have from page 1 to 18 We've already done that in lecture. Let's talk about writing and balancing chemical equations. Thumbs up, people. Do you see that on your screen? Thank you. Now, I'll never ask on a test, what is a chemical equation? But that's a written statement that uses symbols and formulas instead of words to describe changes that happen in a chemical reaction. And I'll never ask you to convention, but the correct formulas, before I go there, I better teach you something. Oh, it's time for Dr. White to be subtle. By the way, if I do a problem or something, you should know that too. All right, let's talk about chemical equations. Let's put a real simple one without actually using chemicals. A plus B arrow C. This is a chemical equation. What does it mean? When you react A with B, you'll make C. At the base of the arrow, these are called the reactants. And there could be one, there could be more. There's one, it's just a reactant. If it's more than one, it's the reactants. Now, since I come from industry and spend most of my many decades in the chemical industry, I will also often say starting materials. So A and B are called the reactants, or I will also call them, which if you're in industry, we call them the starting materials. They're at the base of the arrow always. Now, the plus sign, think of the word and. In a chemical equation, we use the plus to mean and. So this means A and B react together. At the head of the arrow, this is called the product. And if you have more than one, they're the products. C is the products, A is the reactants. So this is a chemical equation, A plus B. You mix the two together, and I'll teach you later on that for chemical reaction, things have to collide, and it makes C. Well, let's look at an example. If I have this chemical reaction, and I just pick that by this chemical equation, what are the reactants? Well, the reactants or starting material are always at the base of the arrow. So the reactants for this chemical equation are hydrogen gas and oxygen gas. What are the products? The products are always at the head of the arrow. And in this case, this is the product. And the product is, in this case, water. And since Dr. White likes to share,
Can you just tell me we have 2 hydrogen and 2 oxygen, right? And then we have only 2 hydrogen, so it shouldn't be.
I haven't got the balance yet. You're ahead of
Okay.
me. Yeah, which is a good thing, but I like to do things stepwise, okay? what one of your colleagues just asked was about balancing chemical equation. And as soon as I'm done with this, we'll get into that. All right, here's your turn for this chemical equation. Hold on. For this chemical equation, what are the reactants? What are the product or products? Your turn. Not asking anything else. Again, what are the products, what are product, and what are the reactants? All right, remember on the base of the arrow here, these are the reactants or starting materials. At the head of the arrow, these or this is the product. And therefore, to answer my question, the reactants are sodium metal plus, let me do and, chlorine gas, Cl2. What is the product? It is sodium chloride table salt. All right, so that's the chemical equation. Remember, at the base of the arrow are the reactants, at the head of the arrow are the products. Now, when we write a chemical equation, certain conventions, the correct formulas for the reactants, the starting materials, are always written on the left side. We just did that. And the correct formula of products, and those are substances produced called the products, are always on the right side of an equation. The products and the reactants are separated by an arrow, and that arrow is always pointed at the products. Whoa, what's going on here? I don't know, my computer just burped at me. All right. And plus signs are used to separate different reactants and products. And I just showed you that in the two examples. Now, there's a validity check. A chemical equation must be considered consistent with experimental facts. If you take hydrogen and oxygen, react together, you're not going to get sodium chloride. You'll get water. And this is important. There must be the same number of atoms of each kind on both sides of a chemical equation. This is called the conservation of matter law. And what that means is for a balanced chemical equation, it has to have the same number of atoms of each element on each side of, I don't know why there's a question mark, but there shouldn't be on each side of the chemical equation. So for a balanced chemical equation, you have to have the same number of atoms and the same type on both sides. Now, when we balance an equation, an unbalanced equation is brought into balance by adding coefficients, and I'll show you what a coefficient is, to the equation to adjust the number of reactant or product molecules. And I'll talk later, probably won't get to it, about the balance or teeter-totter. All right, let's look at the following. Does everybody see H2 plus O2 equals H2O? Now, if we look at this, it has to be balanced. Notice I have 2 hydrogen atoms here. I have 2 oxygen atoms here. On this side, I have 2 hydrogen atoms, 2 times 1, and here, 1 times 1, 1 oxygen. This is not balanced. There should be 2 oxygen or the same number of each atom on each side. Well, the number in front, and when there's no number, it's number 1. This is called the coefficient. And you cannot change the chemical formula, but you can change the coefficient. So if I have 2 oxygens here, how do I get to 2 oxygens here? I change the coefficient. And now 2 times 1, I now have 2 oxygen. But I have 2 times 2, I now have 4 hydrogen. Well, I have 2 oxygen here, but I only have 2 hydrogen, and that has to be 4. So what do? I can't change this to some other formula, but I can change the coefficient. And to get the 4 hydrogens, it'd be 2 times what? 2. 2 times 2 is 4 hydrogen. And if we look on both sides, let's check. It's like balancing a checkbook. I have 4 hydrogen, 4 hydrogen, 2 oxygen, 2 oxygen. This is now balanced. And the balanced chemical equation is 2 hydrogen atoms or molecules react with 1 oxygen. When there's no coefficient, then you assume that's the number 1 to make 2 molecules of water. And this is now balanced. And this is a skill you should have, and we will work on next week. Because if I look at the clock, we're just about out of time. Wow, time flies when you're having fun with chemistry and Dr. White. Now, remember, tonight I'll have my office hour, new office hours from 6 to 7:15, same Zoom login. And don't forget, there was a lab due yesterday. If you're having trouble, I'll let you hand it in late, but come to my office hour tonight, but you need to get it next couple of days. I won't start grading it until the weekend. And don't forget, do the practice problems, keep up. And with that, I'm gonna end up a whole 30 seconds early. Shh, don't tell anybody. And actually, I don't have to do this. I just have to do office hours, but I'm helping you out. With that, I'm going to say, Gang gesund. Stole that from Granny from the Beverly Hillbillies. Gang gesund. Goodbye. Have a nice rest of the day, rest of the week. And if I don't come to my office hour tonight, I'll see you on Monday. Bye now.